Let's take a look at evaluating limits and the properties of limits. So first of all, I have 7 equations here, and you should be able to easily visualize the graph of each of these equations. Then we're going to take a look at the limit of f of x, each of these different f of x's, as x approaches -3. All right, so to start, let's take a look at the graph of f of x equals 3. You know that to be a horizontal line at y equals 3. And if we take a look at where x equals -3 on each of the graphs, we're going to see what happens as we approach x equals -3 from the left, and what happens as we approach x equals -3 from the right on each of these functions. So for the first one, which is a horizontal line, we are always at a y value of 3. So the limit as x approaches -3 on the graph of y equals 3 is 3. Okay, second equation, y equals x. We know that to be the line y equals x passing through the origin. As x approaches 3 from the left, and as x approaches 3 from the right, what y value are we getting close to on the function? The limit as x approaches -3 on the function y equals x is equal to -3. All right, 2x. We know that to be a line passing through the origin, steeper than the line y equals x. We know as we walk along the graph from the left of -3 and from the right of -3, the y value we are getting close to is -6. So the limit as x approaches -3 on the function 2x is -6. All right, next equation, y equals x squared. We know that to be a parabola with a vertex passing through the origin. As we approach -3 for x on the left, and as we approach -3 for x on the right, our y value is approaching 9. So the limit as x approaches -3 on the function x squared is 9. Now if we look at these first 4 examples, they're all pretty simple functions, but every time we found a limit, the y value of the function was the limit value. So I'm just going to make a little note. Most of the time, the limit is the y value of the function as x approaches whatever number you want to approach. Okay, let's take a look at number 5. We have the parabola x squared plus 2x minus 3. I know the y-intercept is -3. I know this factors into x plus 3 times x minus 1. Therefore, we have zeros at -3 and +1. Drawing that parabola, roughly, here we go. As x approaches -3 from the left, and as x approaches -3 from the right, what y value is my function approaching? The limit as x approaches -3 on this function, I'm just going to call it f of x, is 0. Next parabola, x squared minus 2x plus 3. Well, this parabola, I think I want to change this to be a -3 instead of a +3. So this is going to factor into x minus 3 times x plus 1. Okay, the zeros of this parabola are at -1 and +3 with a y-intercept of -3. It's kind of just like the last parabola, just doing a little reflection here. All right, so we have zeros at -1 and +3, y-intercept at -3. What is the limit as x approaches -3 from the left? Oh, well, -3 is way over here somewhere. So as we approach from the left and as we approach from the right, what y value do we get close to? Well, I don't know. But most of the time, the limit of the function is the y value of the function. So let's plug in -3. So I'm going to say the limit as x approaches -3 on x minus 3 times x plus 1 must be -6 times -2. Where did I get that? I plugged -3 in for x. -3 minus 3 is -6. -3 plus 1 is -2. -6 times -2 is positive 12. I could have also plugged it into the original function and said -3 squared is 9 minus -2 times -3, so that's plus 6, and then minus 3. So that's 9 plus 3 is 12. All right, last one. We have a rational function. What do you know about this rational function? Because you're becoming pretty good expert at this. What is my horizontal asymptote? Look at the dominant over dominant. The dominant over dominant reduces down to 2. I have a horizontal asymptote at y equals 2. What is my vertical asymptote? Look at the denominator. When is the denominator equal to 0? I can't divide by 0. That x value will be the the vertical asymptote. Okay, next, what is my y-intercept? Well, let's see. Plug in 0. I'm going to get 0 over 3. That's 0. So I know the graph passes through 0, 0. The graph must fall in this region and this region, meaning when we do the division process, we're going to get 2 plus some negative number over x minus x plus 3. Okay, so it's going to be a negative 1 over x looking graph. Okay, let's take a look at this one from the limit perspective. As I approach -3 from the left, my y value goes to infinity. As I approach -3 from the right, my y value goes to -infinity. We've got a problem. Since the left-hand limit does not equal the right-hand limit, the limit as x approaches -3 on this function does not exist. Okay, we're going to use these examples to look at the properties of limits. So this might look a little scary, but don't freak out. All right, we're going to work our way through this. So first of all, let's take a look. We have numbers c and k, or values c and k. C and k are real numbers. Okay, great. So c could be 2 or -5 or whatever. Then we have the value n. N is going to be a value greater than or equal to 0. Okay, hold that thought. Now we have f and g. F and g are functions. So that's like f of x and g of x. Okay, these functions have limits as x approaches c. So we're going to say the limit as x approaches c on the function f of x is some value L. The limit as x approaches c on the function g of x is some value M. Okay, let's put all this together and then we're going to do some examples along with it so you can see how they actually work. So the first one, the constant rule. It says the limit of a constant k as x approaches c is just the value k. All right, we've looked at this. That's just like this example right here. The limit of the constant 3 as x approaches -3 was 3. Okay, so for example, the limit as x approaches 2 on the constant y equals 7 graph is just 7. Great. So the limit of a constant is a constant. Let's take a look at the identity rule, number 2. The limit of the identity function y equals x as x approaches c. Well, if y equals x and x approaches c, then y must equal c. All right, so the limit of x as x approaches 2, y equals x. When x is 2, y is 2. So the limit of the identity function is always the x value you're approaching. All right, the coefficient rule. The limit of a coefficient times f of x is the same as the coefficient times the limit of f of x. Since the limit of f of x is L, we know the answer to this question is just the coefficient k times L. So let's take a look at our example. The limit of the coefficient 3 times the function x as x approaches 2 is the same as 3 times the limit of x as x approaches 2. Well, we know from the previous question or example, the limit as x approaches 2 on the function x is 2, so this turns out to be 3 times 2, or 6. Remember in the previous slide, I said the limit is most often the y value. What would be the y value on the function 3x as x approaches 2? Well, it would be 6. All right, next rule, the sum rule. The limit of f of x plus g of x as x approaches c is the same as the limit of f of x as x approaches c plus the limit of g of x as x approaches c. So let's take a look at our example. The limit of 3x plus 7 as x approaches 2 will be the same as the limit of 3x as x approaches 2 plus the limit of 7 as x approaches 2. That's 6 plus 7, or 13. If we look back and we say the limit is most often the y value, what do you get when you plug 2 into 3x plus 7? Well, you get 6 plus 7, which is 13. All right, I'm not going to go through the difference. You know that the sum and the difference are really doing the same thing. So, the limit of 3x minus 7 as x approaches 2 would be the same as the limit of 3x as x approaches 2 minus the limit of 7 as x approaches 2. That's going to be 6 minus 7, or negative 1. Okay, hopefully you're getting the hang of this stuff. The limit of f of x times g of x as x approaches c will be the same as the limit of f of x as x approaches c times the limit of g of x as x approaches c. So our example says the limit of 3x times x plus 1 as x approaches 2. So I'm going to look at those two pieces separately. The limit of 3x as x approaches 2 is 6. The limit of x plus 1 as x approaches 2 is 3. 6 times 3 is 18. Next, the quotient rule. The quotient rule, we just have to be careful that we're not dividing by 0. Okay, so the limit of f of x divided by g of x is the limit of f of x divided by the limit of g of x, provided that the limit of g of x does not equal 0. So take a look at our example. We have the limit of 3x over x plus 1. We're going to look at the limit of the numerator, which is 6, over the limit of the denominator, which is 3, and 6 over 3 is 2. The last one is the power rule. The limit of f of x to the nth power as x approaches n will be the same as the nth power of the limit of f of x. So take a look at the limit of 3x squared as x approaches 2. That will be the same as the limit of 3x, finding that limit and squaring it. So when I find the limit of 3x as x approaches 2, that's a 6. And when I square it, I get 36. Now if I look back at the original expression that I'm taking the limit of, that's the same as 9x squared. So that could be the same as 9 times the limit as x approaches 2 of x squared. Well, what's the limit of x squared as x approaches 2? That's 4. And 9 times 4 is 36. So these are the same thing. Hopefully you're feeling pretty confident about how to use limits to break up your expression, if you need to evaluate the limit. Last thing is, we have verbal descriptions of what these limits are saying. So for example, I'll do the product rule. The limit of the product of two functions is the product of the limit of two functions. The limit of the product of two functions is the product of the limit of two functions. Good? The limit of the difference of two functions is the difference of the limit of two functions. So read through these English versions of the rules, see if they make sense, but hopefully you'll be able to evaluate limits pretty easily. Thanks for joining me. We'll get back to limits pretty soon.